We now have two very powerful ways of estimating age distributions. We've introduced the tracer experiment, and we've also introduced the mass balance. And we have the two results that E of theta can be obtained by experiment by dividing the tracer concentration measured at the exit by the area under that same curve. So that's our E of theta, and we have that I of theta is simply 1 over tau 1 minus the integral 0 to theta for E of theta in theta. And we can estimate the age distribution inside and the age distribution at the exit point. And in fact, before we started applying such methods, we had discussed two reactors. So we had discussed the CSTR, so the perfectly mixed reactor. So we have a flow through this reactor, and we have vigorous mixing in here, so we have the same concentration throughout and the same age distribution throughout and equally at the exit. So that's the perfectly mixed case. And then we also have the perfectly not mixed case. So perfectly not mixed in the sense that all the fluid elements stick together in plugs of fluid. So we've got plugs of fluid chugging along here. And we said in each case that we could apply some kind of physical intuition to predict what those age distributions might look like. So in the case of the CSTR, we said because the younger fluid elements have less time to the time of exposure to the event of exiting from here, that the age distribution inside the reactor would look something like this, that we would have, sorry, that try and smooth that. So that's the age distribution that we expect. We expect to see more young particles here, and as you consider greater ages, there's less the likelihood that they will survive to greater ages, given that there's always this event of withdrawal, things being withdrawn from the reactor. There's a reduced probability that you will survive to those great ages. So that's the kind of age distribution we're expecting there. And we did say that we expect in that case that the age distribution in here is the same as the age distribution in there. So in that case, we have this kind of expectation that these two will simply look the same. So we'll have the same kind of curve here. And then we said in this case with the plug flow reactor that we expect to see at the exit point all our fluid, so because everything stays together as a plug, everything will take the same period of time to pass through this reactor, and we had defined the space-time there. So it's all going to exit at one instant here where the age will be tau. So in this case there's tau, and so we said we would use some kind of spike function here to denote that everything's exiting at that one time. And we also said that at the exit point we expect to see that, sorry, not at the exit point, inside of the reactor we would retain everything until we reach the exit point, at which point everything exits. So beyond age tau we don't expect to see anything in the reactor. Let's draw that better. So beyond age tau we don't expect any contribution at the exit point, but before we reach tau we will have equal amounts of these young and old ages and ages in between. So we have equal amounts of all these other ages. So we expect to see something like this in the case of the plug flow reactor. So that's the pattern we are expecting to see. For the CSTR, we are expecting this kind of drop-off, and they'll be equal there. In the plug flow reactor, we are expecting to see this kind of box function and the spike here. So in this case, the two distributions are quite different as compared with here, where they are the same. So we want to now apply these balances or these relationships that we've developed and see if we can get these same relationships. So let's derive it. So let's look at the CSTR. I'll just draw a slightly better looking one here. add a little stirrer. And here's our stream in and stream out. And what we're going to do now is write a balance on this reactor. And see, we know that this refers to the concentration of tracer. So we were taking the concentration of tracer curve and dividing by its area. So we will now try to predict this concentration. So this concept is something to think about a little bit, because this was intended to be on some experiment, right? We intended that we'd do some experiment and we would take the results of that experiment, these concentrations that we measured, and divide that by the area. But what we're doing now is trying to predict this concentration. And so if we can predict this concentration, then that means we've got the function without having to measure it. And this relationship still holds, right? It doesn't matter to this relationship whether we got this function by measurement or by some kind of modeling exercise. So let's try and do that. Let's try and get this function by modeling the reactor. So to do that, let's write a mass balance, and we're going to write this mass balance on tracer. So in this reactor, we expect to have tracer molecules floating about, right? Like in the practical that you might have done, you've got water flowing through the reactor and you inject salt at some point and you measure the conductivity at the exit. So in this case, these tracer molecules might be salt, and we are assuming that it's going to be injected in, so there'll be a pulse of salt coming into the reactor, and after that we don't put any more salt in the reactor. So that's the kind of function we're expecting for the injection of salt. So let's write the balance on that. So we can write rate of change of moles of salt. So let big N be the number of moles of salt. Then that will equal the flow rate in to the reactor of salt minus the flow rate out. And then we would normally, it's almost a reflex to us by now to write reaction rate times volume. But of course, this is just a tracer. So the tracer is not reacting in this in the reactor. So the tracer is just not reacting there. That's not the purpose of the tracer. So we don't have to write a reaction term here. So we can go further. We can write the rate of change, and then number of moles will be the concentration, and we'll call A. We'll use A for salt. So that concentration multiplied with the volume of the reactor, that's the number of moles of salt in there. And then the flow rate in of salt, it's a bit of a weird function. It's that spike function. So for now, we'll just call it Ca in at some time times the volumetric flow rate. So we've got some flow rate here, Q, which is constant and steady and equal, in equals out, and then the volume of the reactor is V. So that's there, and then the flow rate out. Now remember, this is a CSTR, so perfectly mixed everywhere. So we've got some concentration that applies inside the reactor Ca, and so we've got the same concentration of salt everywhere in the reactor, including points at the exit, so the concentration out there will be Ca as well. So the Ca value we are using here, that refers to the concentration anywhere in the reactor, and that's the same as the concentration at the exit. So we can write here minus Ca, I guess we should say time, times the volumetric flow rate Q. Right. Now, the volume here is a constant, right? We assume that if this is a gas, it's going to fill the whole space, or if it's a liquid, then the liquid height is constant. So the volume we are treating as a constant. We can take that out as a constant. And then looking at this function, you can see we have something of an inconvenience here, in that this inlet concentration of salt is a strange function. We've got this spike here, and we'd rather just avoid having to deal with the spike. So we will do that by saying we will consider the time only after the injection time. So here we are injecting salt into the reactor at, you can say, T0, we'll call it T0. So for time greater than T0, we aren't injecting any more salt into that reactor. So we only inject at T0, we don't inject any salt again after that. And so we will consider Ca in to be 0 after that. And just be careful, although we aren't injecting salt anytime after T0, the moment salt does enter, right, at T0 some salt enters, then it's going to mix everywhere in that reactor. And after time T0, there will still be salt held up in that reactor, and it will take its time exiting. So depending on the mixing pattern, well, it's perfect mixing here. So it's going to take some time to exit, but in terms of the inlet flow, we aren't feeding any more salt. So salt has mixed its way around in this reactor, and that's going to take a time exiting, but there isn't any more coming in after T0. So we can rewrite this. We can maybe we can divide by the V as well. So we can write ddt of Ca. So Ca is not 0, right? A is the salt again. So this concentration is not 0 because we still have some salt mixed around in here. That's equal to, and we've gotten rid of this. We said this is 4T more than T0, so that's a 0 there. And then minus Ca Q over V. And we have introduced already the definition that the space-time is equal to the volume over the flow rate. So this is effectively Ca over tau. So, well, let's just write it that way. Ca over tau. So Ca over tau here. And this is a simple first order ODE, which we can solve. We should well recognize the solution to this by now, so we can just write down the solution. We know that's going to be Ca is equal to Ca naught times exp of minus T over tau. Right, and okay, let's leave it like that. So this is telling us this is how the concentration of the salt is going to change with time, and what we really want is E of theta. So E of theta equals, and we are going to make the usual translation. So we'll say let T0 equal 0. So T equals theta, and also we know that everything gets older at the rate of 1 second per second. So d theta dt equals 1. So when we write E of theta, we can say that Ca of theta over the integral Ca in theta, and this is the area under the curve for all possible values of theta, so we should say here 0 to infinity. So we have this function Ca of theta. Well, it was t here, but we made this translation. So we have this function Ca of theta, and let's try and evaluate this denominator. So we can write here integral 0 to infinity for Ca of theta in theta is equal to the integral 0 to infinity for Ca naught exp of minus theta over tau, and that's integrated in theta. And just lighten that, and then that's equal to, and we can see Ca naught is actually the initial concentration. So for the time just after T naught, there's some initial concentration there, Ca naught. So that's not going to change with age. That was the initial concentration. So Ca naught out there, and then we need to integrate this this function, right, which is a function of theta. So the integral of the exponential of a variable times some coefficient is of course equal to 1 over that coefficient times the exponential function. So this is times minus tau exp of minus theta over tau, and we are integrating over the limits from 0 to infinity. So from 0 to infinity, and that's equal to, if we keep these constants here, so let's just write it like this, and here we've got exp of minus infinity over tau, so that's going to be an infinitely large negative number, the exponential of that, which we know is the 0. So that's going to be a 0 minus, and then exponential of 0. So the lower limit will have a 0 there, so exponential of a 0 we know is a 1. So this has worked out to Ca0 times tau. Right, we just take that minus 1 and times that minus, and that's what we have there. So we can apply this result here in the denominator, and we can look at our Ca of theta function. So you've got Ca0 here, so that Ca0 can cancel with that. Well, let's just write it. So Ca0 exp, and then we're using the variable theta instead of t here, so that's exp of minus theta over tau over, and then the denominator Ca0 tau, and we can see Ca0 can cancel, leaving us with 1 over tau exp of minus theta over tau. So that's our E of theta. And look at this function. That's an exponential decay, so that's obviously looking like this. So E of theta, an exponential decay here. And if you look at what we expected, right, we said because of the nature of the mixing here that we would get some kind of, we didn't know what shape that was, we knew it was decreasing like this. So we have correctly predicted E of theta so far. So we've got E of theta. Let's try the other ones. The next step then would be to try and predict I of theta. Okay, so we've got E of theta. E of theta is equal to 1 over tau x of minus theta over tau. And what we want to do now is determine what I of theta might be. So I of theta has a relationship with E of theta, which is 1 over tau 1 minus the integral 0 to theta of E of theta in theta. So we can apply E of theta in there. So we can write 1 minus, and you can see this tau is a constant with respect to theta, so we can leave that out here, 1 over tau, and then the integral of this with respect to theta is going to be, and you've got this minus tau, minus 1 over tau in here as the coefficient, so in terms of the integration, that's going to be 1 over the coefficient of the variable, so that's minus tau exp of minus theta over tau, and the limits here 0 to theta, that's equal to 1 over tau and 1 minus, and okay, let's just do it step by step. So at theta, this is going to be exp of theta, theta equals theta, so there isn't a special value there. It's not like it's going to infinity or 0, so we have to just retain that term as it is. So we'll write this as minus tau exp of minus theta over tau, and where this theta is the theta of the argument here, right? In this case, theta was a theta that depended on the range. This theta is actually the theta of the argument. So that's the upper limit, and then minus the lower limit. So when we apply a 0 here, this is exp of 0, so that's a 1. So that works out to a minus tau. So that's minus tau. And so we've got 1 over tau, and it's 1 minus. And if we multiply this out, this tau can cancel, leaving us with the plus exp of this. So that's exp of minus theta over tau. And then here we've got, yeah, actually I needed to close this bracket, right? So there's a closed bracket there. So this is a plus tau, and we've got plus tau times minus 1 over tau. So this works out to a minus 1. And so 1 minus 1, and then 1 over tau exp of minus theta over tau. And that's our I of theta. And if you compare that with what we had up here, look, we've got the same function. So in this case, we can see E of theta equals I of theta. And we expected this. We said this is a perfectly mixed reactor, so we'll have the same age distribution inside the reactor as we have at the exit point, and it turns out that when we just follow strictly the rules and develop the model, that we do get that same result. We also find that we are getting the right shape of curve. Remember, we said that E of theta and I of theta are some sorts of functions that are decreasing in value like that, and that is what we are seeing. So the rigorous mathematical model does agree with our expectation for our CSTR. Right, so that's the RTD for the CSTR. And the next step, of course, looking at the plug flow reactor. So we've got plugs of fluid here. This is my kind of shorthand notation for plug flow reactor. And we know that the space-time is tau, so it takes tau time units to pass through this reactor. So if we are going to spike tracer in here, and in fact let's do it a bit more carefully. So at the inlet point we can say C in, there's some T naught, the time at which we spike the tracer in. Sorry, time that we spike the tracer in, that's going to look like that. And then that tracer is going to enter, of course, the first plug of fluid in there, and then that plug is going to go chugging along, and it will move through at velocity u, and it will exit after tau time units. So at the exit point we are going to see, so if that's C out, if this was T naught, and if this is T naught plus tau, then that's where we'll see the same spike, and it is actually the same spike. So I'm just gonna cheat a bit and copy this one. So that's what the exit stream will look like. So we'll see nothing. We'll see a sudden spike of tracer of salt, if it's the salt water example, and nothing again after that. So we can propose a nice easy model in this case. We can say, in fact, we need to think about how to represent the spike. And in fact, it's not a spike. This is rather a special case where we have absolutely nothing until a certain point where we have everything. I know it sounds a bit silly the way I'm saying it, but so we have nothing at this point. Sorry, at all points before this point. That's a 0, intended to be a 0. And then there's one instant where everything is entering the reactor. So there's one instant where it enters, and then nothing again enters afterwards. And of course, this is an idealization. In reality, a human being operating a syringe is always going to take some finite time period to do this injection. But what we are referring to here is more like a theoretical tool. So we are imagining an instantaneous injection here, which is not something you can do in the real world. Everything takes a finite period of time, but that's our theoretical tool. And so we need this kind of jump discontinuity. And in fact, there is a way to do this. In physics, we have what's called the Dirac Delta function. So we're going to use this Dirac Delta function for this jump discontinuity. So more about that in a second. So we do have this effect here. The effect is that we are delaying our pulse by this time period tau. So we can directly write down our expectation of the exit RTD. Sorry, here. So we can write down what we expect in terms of the exit RTD. We can say here that the exit age distribution is going to look like this, that everything exits at time tau. So if we pick a tau here, we can say we'll see nothing at the exit until tau, where we'll see everything, and then after that we see nothing again. So it's that kind of jump discontinuity that we have. Furthermore, E of theta, the integral E of theta, is a fraction of fluid elements, right? So if that's a fraction, then we want that when we integrate under the strange looking function, that it must come out to 1. So if we integrate over all possible values of E, we want this to equal a 1, which seems like kind of a difficult thing to do, given that we've got in effect a single point or a single instant here. So that means everything is concentrated into this one point. And for this reason, this point actually goes off to infinity. So maybe another way to look at it is, if we have some graph like this with not a discontinuous jump, but some finite spread, and let's say the area under this was 1. Now, if you wanted to maintain this area being 1 and you wanted to make this narrower, so let's say the distribution was getting narrower for some reason, then of course to maintain that same area, your next curve would have to be something like that. And in fact, it's not well drawn. It would have to be much sharper than that. So you can see the effect of trying to squeeze all your population members into a tinier and tinier space is that you are concentrating them into one space. So the concentration shoots up as you do that. So in a similar way here, we are doing a very extreme form of that. We are concentrating it all into one single value in a continuous space, right? Theta is a continuous variable, but we are somehow claiming we are going to concentrate it all into one single value of that theta. So this value is shooting off to infinity, but it's not the kind of unknown infinity that we normally think of when we write infinity. It's an infinity such that this area is equal to 1. And in physics, this has been this is a problem that that arose in trying to describe some other discontinuities. There's probably something to do with the Big Bang theory and so on. But we have this nice function, the Dirac Delta function, which is defined as follows. So the Dirac Delta function is defined such that we have a value of 0 for x not being 0, and it tends to infinity for x being 0, such that the integral under the Dirac delta function is equal to 1. Right? So that's the nature of the function. So if this is 0 here, then it's 0 everywhere except at 0. So there's an empty point there. And so we've got zeros here except at 0, where it shoots off to infinity. And it shoots off in such a way that if you integrate under that point, you'll get this value of 1. So that's this Dirac delta function. And you might read out of interest about the C of Dirac. And okay, so the Dirac delta function is what we're going to use. In our case, it's not centered on 0, it's centered on tau. So to develop our model, we are going to simply state here E of theta is equal to Dirac delta theta minus tau. And that accomplishes straight away what we want. So everything is concentrated into this one instant tau, at which point it's going off to infinity. So that's our model. That's E of theta for us. Okay, so that's one side of it. So we want to write I of theta is 1 over tau 1 minus the integral 0 to theta of E of theta in theta. So let's apply for the plug flow reactor. So for the plug flow reactor, E of theta is the Dirac delta function. So this is 1 over tau 1 minus the integral 0 to theta of Dirac delta function theta minus tau in theta. So that's equal to 1 over tau. And let's think about this. So if we have this integral, and let's just plot Dirac delta function. So let's plot Dirac delta function like this. So this is tau here. So this is not actually Dirac delta function. This is Dirac delta at theta minus tau. So that's theta. So we've got the discontinuity here, and it's 0 up to that point. So if we are integrating, if theta is less than tau, you can see there won't be any area contribution from here. This is all 0. So if you integrate under 0, you get back a big fat 0. So it's staying on 0 there. So this is going to be 1 minus 0 1 minus 0 for theta less than tau. Right, and then the moment you reach tau here, you've suddenly got this area of 1 that's been contributed. So when you reach the 0, when you reach the tau, this is area, right? This is integral, and if you are on tau or just past tau, this is going to be the area under that point, and we know the area under that point is a 1, so this is 1 minus 1, which is 0. So this is equal to 0 for theta greater than or equal to tau. Right, so for the PFR, we now have the model. We have that I of theta is equal to 1 over tau for theta less than tau. And it's equal to 0 for theta greater than or equal to tau. And if you were to plot this, I of theta, we've got a tau here, so it's 1 over tau, and we know tau is some finite number, some finite positive number, so it's going to be somewhere there, and then it drops to 0 just past the tau. So that's there, and that's there. Ugh. Okay, so that's there, and it's 0 after that. Okay, so that's our model then. So applying the mathematics, we get these two functions for E and I of theta. And if you look back to our expectation, just trying to find it. So we said we expected this, right? We said for the plug flow reactor, we are expecting everything to come out at one instant, and we are expecting equal proportions of each of the existent ages there. So everything is flowing nice and regularly there. We used that logic at that time to reason out that we'll have equal amounts of all of that. And that is the result we are getting here. So the maths and the methods we've derived do agree with our physical intuition as well.